Hello! Today we're going to explore a fundamental concept in number theory, prime factorization. By the end of this video, you will be able to define prime and composite numbers, understand the fundamental theorem of arithmetic, and use two different methods to find the prime factorization of any natural number. Let's start with the building blocks. What are prime numbers? A prime number is a natural number greater than 1 that has exactly two distinct positive divisors, 1 and itself. In other words, it can only be divided evenly by 1 and itself. Let's look at some examples. The number 2 is prime because its only divisors are 1 and 2. The number 3 is prime because its only divisors are 1 and 3. The number 5 is prime because its only divisors are 1 and 5. The number 7 is prime because its only divisors are 1 and 7. So, 2, 3, 5, and 7 are all prime numbers. Notice that 2 is the only even prime number. Now, what about numbers that are not prime? A composite number is a natural number greater than 1 that is not prime. This means it has more than two divisors. For example, the number 4 is composite because its divisors are 1, 2, and 4. The number 6 is composite because its divisors are 1, 2, 3, and 6. The number 9 is composite because its divisors are 1, 3, and 9. So 4, 6, and 9 are composite numbers. They can be formed by multiplying smaller numbers together. There's one special number we haven't mentioned yet, the number 1. The number 1 is neither prime nor composite. It's a unique case because it only has one divisor, itself. It doesn't fit the definition of a prime number, which requires exactly two divisors, nor the definition of a composite number, which requires more than two. So, to recap, we've defined prime numbers as having exactly two divisors, composite numbers as having more than two, and the number 1 as being in a category of its own. These are the building blocks for our next topic. Now that we understand prime and composite numbers, we can talk about the main idea behind prime factorization. This idea is so important in mathematics that it has a special name, the fundamental theorem of arithmetic. The theorem states that every natural number greater than 1 can be written as a product of prime numbers in exactly one way, ignoring the order of the factors. Let's break that down. It means that any number, like 12, can be broken down into a unique set of prime numbers multiplied together. For 12, that's 2 times 2 times 3. No matter how you start, you'll always end up with the same prime factors. You could start with 12 equals 2 times 6, or 12 equals 3 times 4. Either way, you'll find the prime factors are 2 2's and 1 3. This theorem is incredibly powerful. It tells us that prime numbers are the fundamental building blocks of all other numbers. Think of them like the atoms of the number system. Our goal now is to learn how to find these unique prime factors for any number. We'll explore two common methods for doing this. The first method we'll learn is called the factor tree method. It's a very visual way to break down a number. Let's find the prime factorization of the number 30 using a factor tree. We start by writing the number 30 at the top of our tree. Now, we need to find any two numbers that multiply together to give us 30. It doesn't matter which pair you choose. Let's pick 3 and 10. We write 3 and 10 at the end of these branches. Now we look at each of these new numbers. Is 3 prime? Yes, it is. So we circle it. This branch is finished. What about 10? Is 10 prime? No, it's composite. So we need to break it down further. We draw two more branches from 10 and find two numbers that multiply to 10. Let's use 2 and 5. Now we check these new numbers. Is 2 prime? Yes. So we circle it. Is 5 prime? Yes. So we circle it. Both of these branches are now finished. Our tree is complete because all the numbers at the ends of the branches are prime. The prime factorization of 30 is the product of all the circled numbers. So, the prime factorization of 30 is 2 times 3 times 5. This is the unique set of prime numbers that multiply to 30. Let's try another one. Let's find the prime factorization of 48. We start with 48. Let's break it into 6 and 8. Neither is prime, so we continue. 6 breaks into 2 and 3, both of which are prime. 8 breaks into 2 and 4. 2 is prime, but 4 is not, so we break 4 into 2 and 2, which are both prime. Now we collect all the circled prime numbers. We have 4 2's and 1 3. So the prime factorization of 48 is 2 times 2 times 2 times 2 times 2 times 3. This method is great for visualizing the process of breaking a number down into its prime components. It shows how any number can be built up from these prime building blocks. Now let's look at a second method, which is often more efficient for larger numbers. This is called the division method. The division method involves repeatedly dividing the number by the smallest possible prime number until you are left with 1. We use a special division symbol that looks like an upside-down long division bracket. We write the number we want to factor, 72, inside this bracket. Now we start with the smallest prime number, which is 2. Can 72 be divided by 2? Yes, it's an even number. So we write 2 on the outside and the result, 36, underneath 72. Now we repeat the process with 36. Can 36 be divided by 2? Yes. We write another 2 outside and 18 underneath 36. We continue with 18. Can it be divided by 2? Yes. We write another 2 outside and 9 underneath 18. Now we have 9. Can 9 be divided by 2? No. So we move to the next smallest prime number, which is 3. Can 9 be divided by 3? Yes. We write 3 outside and 3 underneath 9. Finally, we have 3. Can 3 be divided by 3? Yes. We write 3 outside and 1 underneath 3. We stop when we reach 1. The prime factorization of 72 is the product of all the prime numbers on the outside of the bracket. In this case, it's 2 times 2 times 2 times 3 times 3. Let's try one more, a slightly larger number. Let's find the prime factorization of 150. We start with 150. It's even, so we divide by 2 to get 75. 75 is not even, so we can't divide by 2. Let's try the next prime, 3. The sum of the digits of 75 is 12, which is divisible by 3, so 75 is divisible by 3. 75 divided by 3 is 25. 25 is not divisible by 3. The next prime is 5. 25 is divisible by 5, giving us 5. Finally, 5 is divisible by 5, giving us 1. We're done. The prime factorization of 150 is 2 times 3 times 5 times 5. This method is very systematic and ensures you find all the prime factors. Let's quickly recap what we've learned today. We started by defining prime numbers as numbers with exactly 2 divisors, and composite numbers as numbers with more than 2 divisors. We also noted that 1 is a special case, being neither prime nor composite. Then we learned about the fundamental theorem of arithmetic, which states that every number greater than 1 has a unique prime factorization. This means prime numbers are the basic building blocks of all other numbers. Finally, we practiced 2 methods for finding this factorization, the visual factor tree method and the systematic division method. Both methods will always lead you to the same unique set of prime factors. Understanding prime factorization is a key skill in mathematics. It's used in many areas, from simplifying fractions to cryptography. You are now equipped to break down any natural number into its prime components. Thank you for watching.